In this video, we will discuss the solution to problem F from Atcoder Beginner Contest 335. This is a summary of the problem. Each cell can affect a cell that is at a distance which is a multiple of AI, the number written on that cell. You can continue this process any number of time. At the end, you need to find out the number of unique subsets of affected cells. You can find the code, slide, and the practice problems in the comments section on YouTube. We need to find the number of subsets that contain all black elements. Notice that there is a bijection between subsets and subsequences. Hence, we can just find the number of subsequences that contain all black elements. How is this definition helpful? Notice that all the elements in a subsequence are ordered. Hence, it is easy for our brain to figure out pattern amongst the elements. This is still a large problem space. So let us add some restrictions so that we have a smaller area to work with. We are interested in finding out the number of subsequences with all black elements that end at a particular index I. Let us call this value as dp of I. Notice that the subsequences or the subsets that we are interested in has to end at some particular index. Therefore, the final answer would just be the summation of dp of I over all indices. How to find the dp value of the pink cell? By definition, this is the last element of the subsequence. Then you can make some choices on the second last element of the subsequence and sum up those dp values to get the dp value of the pink cell. This technique is known as receiving dp. Now suppose that you already knew the dp value of this pink cell, and of course that dp value represents the number of subsequences that end at the pink element. Now what happens when you append an element to all of those subsequences? For example, what happens when you append a blue element into all of the subsequences that end at the pink element? You can notice that it will create a subsequence that will end at the blue element. Therefore, dp of blue would be equal to dp of pink plus some contribution from other elements. So if we keep on iterating the elements from left to right, and every time we encounter an element, instead of worrying about populating the dp value of that particular element, we can instead focus on updating the dp value of the appended elements. So if we keep doing that, by the time we encounter the blue element, we will have the correct dp value of the blue element populated. So this technique is known as distributing dp. There is just one rule for distributing dp. There should be no partial contribution. It means that if you do not know the correct dp value of a particular index, you should not add the contribution of that index to other elements. At the start of the algorithm, we know for certain that the dp value of the green cell, which is 1, is correct. Then we can propagate the dp value of this green cell. In the next iteration, can we propagate the dp value of the second cell? Yes, we can, but first of all we need to prove that this dp value is now correct. Suppose the number written on the first element is 2. Then you can move 2 steps and append this element to create a subsequence ending at this element. So you add the dp value of green here, and then you repeat the process, that is you keep on moving 2 steps and add the contribution. Then can you now see that the dp value of the blue box would be correct, because all the choices are now exhaustive. It means that if a sequence ends at a blue box, then the last second element of a sequence has to be to the left of it. And since we already processed all the elements to the left of it, it means that by the time we reach the blue box, we will have the correct value, dp value of the blue box. So suppose the blue box contains the number 3. Then you can move 3 steps, add the contribution of the blue box, again move 3 steps, add the contribution, and continue. Using a similar argument, you can show that the dp value of the orange box is now correct. Suppose that the number written on it was 4. Then you can move 4 steps, add the contribution of the orange box, move 4 steps, add the contribution of the orange box, and so on. Same for the white box. Now the dp value of the white box is correct, and suppose that the number written on it is 5. Then you can move 5 steps and add the contribution of the white box over here. The code is pretty straightforward. You keep on iterating from left to right, and for each I you move ai steps and keep on adding the contribution to the element that is encountered. At the end, you print the sum of all dp values as per definition. Let us look at a simple problem that will act as a motivation for the solution to the original problem. You are given an array and some queries. In each query, you need to add some delta to a particular subarray. After all the queries are done, you need to print the final array. For example, if you had an array of length 14, you need to add some delta on these subarrays represented by these lines. Once all the operations are done, you need to print the final array. You must already be familiar with the classical approach to solve this problem, which is to use a difference array. The benefit is that the range updates will now be converted to point updates, and once all the queries are done, you can instead convert the difference array to a prefix sum array to retrieve the desired array. This approach definitely works, but there are a lot of things going on in the background, such as the difference array and the prefix sum array. So let us look at another implementation that doesn't utilize these concepts, but at least not directly. We will call this idea lazy propagation. First, let us sort all the queries by their left endpoints, since their order does not matter. And second, notice that a subarray query can be transformed into 2 suffix queries, right? You add a delta to this entire range and you subtract a delta from this range. Then you process the elements from left to right. Suppose you are at element 1 and you need to add some delta to all of these elements. So you offload the process. That is, instead of adding the delta to all of these elements, you add a delta to the second element and ask it to push the delta forward. Then when you move on to the second element, you push this delta forward, of course, but then you also have some more deltas that you need to add to all of these elements. So you repeat the same process as before. That is, you add this green delta to this element and ask it to push this delta forward. Similarly, you add this yellow delta to this element at position 3 and ask it to push it forward. Then when you reach the third element, you will see that it has no delta that it needs to push forward of its own, but it has the previous deltas. So it will just pass on the responsibility to 4, right? Pass on the responsibility to 4. And in this manner, instead of iterating over the entire array, every element will now offload the responsibility to its right neighbor, and in the end the constructed array would be the desired array. This approach also has the benefit that every time you arrive at a particular index, after summing up the delta of this particular index, you will notice that this is the correct value of that index. This is not the difference array, not the prefix sum array. This is just the correct value of that index. So this idea of lazily propagating the delta by passing on the responsibility to its right neighbor will be very crucial for us to solve the original problem. Back to the original problem. What if the given array was a permutation? Can you figure out the time complexity of the naive distributing DP that we had written earlier? I'll leave that as an exercise for you. Let me know the answer in the comments. Next, let us assume that all the values in the array are identical. Do you see a way to fill the DP array in O of n? This is some hints. You can pause the video and think about the solution. What if the array only consisted of ones? You can notice that DP of 1 would contribute to all of these elements represented by the blue lines. Instead of manually updating the delta for these elements, you can update the delta for element at index 2 and ask it to push the delta forward. So this is the same lazy propagation technique that we discussed in the previous slides. What if the array only consisted of 2's? You can notice that the black box difference array plus prefix sum array approach will not work over here because there are gaps in between. But the lazy propagation idea will still work because DP of 1 will update these blue lines. So instead of going to all of these elements and updating their delta value, you can instead update the delta value at 3 and ask it to push the delta not one step but 2 steps to the right. Then when you arrive at element 3, there are two kinds of delta that needs to be propagated. One is the orange delta originating from the element 3 and one is the previous delta, the blue lines. So the blue lines, it can just push the responsibility to 5, and for the orange lines it can also push the responsibility to 5, and in the same manner every delta will propagate 2 steps to the right until it goes out of bound. Similarly, if the array consisted of only 3's, you can see that the same logic will work flawlessly. That is, instead of going 3 steps to the right and updating the delta and repeating the process infinitely, you can simply go 3 steps to the right, update the delta over here and ask it to push the delta 3 steps to the right. Similarly for 4's, right? You can see that you need to update these deltas. So you can just push the delta to element at index 5 and ask it to propagate the delta 4 steps to the right. Similarly, if you have all 5's, you can notice that this same technique will work for 6 as well and for 7 as well. So far, we have seen a linear time algorithm to compute the answer when the array consisted of all ones, all twos, all threes, and so on. Now, what if the array can contain any integer? Can you combine all of the n sub-problems that we have discussed? You can see that it is easy to combine all of the sub-problems if you maintain n different slots for each index, so that you can propagate each of the delta value independently. So each index will take its contribution, or basically it will pull all the delta values from each of the slots. Then it will add its contribution to exactly one slot, and then it will push the delta value in all of the slots to its right neighbor. In this matrix, each row corresponds to an index in the original array. and each column corresponds to a delta value. You can notice that these columns are nothing but the n different sub problems corresponding to identical elements that we discussed earlier. If this was your original array, you can see that dp of 1 will propagate 2 steps downwards. But we can also pretend that dp of 1 will propagate a delta value of 0 for this cell, delta value of 0 for this cell, and so on. Then when you go on to the next element, you can see that dp of 2 will propagate 1 step downward. Then when you go to the third element, you can notice that dp of 3 would be the sum of the delta values of all the elements on this row. And once you compute dp of 3, you can notice that dp of 3 will propagate its own delta value, which will move at the speed of a of 3, and then it will also push all of these delta value downwards. So this blue delta will be pushed 1 step downwards, this pink delta will be pushed 2 steps downwards, and so on. The code is simple. For each row, you pull the delta values of all elements on that row. Then you propagate your own delta, which will travel at the speed of a of I. And then after you have propagated your own delta, you need to push the delta that came in from the previous element. So a delta at column j will propagate at the speed of j. So that's why a delta of column j will propagate at the speed of j. And then finally you print the sum of all dp values. Now notice that the delta propagation is O of n per index. This is because there are n different delta values for each row, and each delta value will move downwards in O of 1. So the time complexity for delta propagation is O of n per index. Now notice that there is no scope for further optimization because each cell already moves to its next neighbor in O of 1. So the only option remaining is to cut down on the number of columns or the number of delta values that you have. And this trick that we are going to see is known as the square root trick, wherein we try to cut down on the number of delta values that we need to propagate. Now let us split the delta values into two different sections. The first section would contain all the delta values that are less than or equal to square root n, and the second section would contain all the delta values that are greater than square root n. On the number line, you can visualize that the first section would be very small and the second section would be large as compared to the first section. Then we'll drop all the delta values that are bigger than square root n. This means that in this matrix, we will drop a set of suffix columns from this matrix. But if you drop a set of columns from this matrix, their delta will not propagate using lazy propagation anymore. So that means you need to manually propagate their delta. Also recall that a delta from column j propagates at a speed of j. So delta from column 2 will propagate at a speed of 2, delta from column 3 will propagate at a speed of 3, and so on. So in all of the columns that were removed, the delta value was greater than square root n. So it means that their delta will have a speed greater than square root n. So that means that if you try to manually propagate the delta for each such element, it will cross index n in no more than square root n time, right? Because square root n into square root n is greater than or equal to n. So it means that every time in the array we encounter an element that is greater than square root n, we can manually update all the elements by ourselves instead of relying on lazy propagation, because manually updating all the elements, manually passing on the contribution, will only take O of square root n time, and O of square root n time per index is acceptable. And if we encounter an element that is less than square root n, we can anyway employ the trick of lazy propagation to propagate this delta. So we'll just cut down the suffix columns that are greater than square root n, and we'll manually and we'll propagate the delta of the remaining columns using lazy propagation technique that we have already discussed. And every time we find an element that is greater than square root n, instead of relying on lazy propagation, we'll just manually go to all of its neighbors, all of its corresponding neighbors, and then we'll update the contribution manually, so that every time you arrive at an index, the dp value will of course be the sum of all the columns corresponding to this row plus the sum of all the manually propagated delta values. So this trick is known as the square root trick, which relies on the fact that the numbers smaller than square root n are very small, are small in number as compared to the numbers that are larger than square root n. And all the numbers that are larger than square root n, they will have a speed that is larger than square root n as well. So they will converge to n very fast, right, in at most O of root n steps. For the code, first of all we figure out the square root of n, then we trim down the dimension of the matrix to n cross root n, and the rest of the code remains the same. That is, for each row we sum up all the delta values in that row, and keep in mind that this dp of I already contains the sum of the manually added contribution. Then we check if the current element is greater than root n. If it is greater than root n, we manually update the contribution by going to each of the corresponding neighbors, and keep in mind that this loop will only run root n times. But if it is smaller than root n, we cannot manually go to each of the neighbors, so we rely on lazy propagation. So since the value is a of I, it will propagate at a speed of a of I. Then after we have added the contribution of this ith element, we push all the delta value downwards. Remember that a delta on cell j will propagate at a speed of cell j. Now you can try to run some sample test cases to understand how the delta propagation works for the elements that are smaller than root n as well as for the elements that are greater than root n. And I have also added one practice problem corresponding to the difference array trick that we discussed earlier, and some sub problems of the Atcoder problem that you can access from the Code Forces group. So you can find all the codes and the resources and the group link etc. on CF step.